F5, Alt-Tab, выключить. Он у вас правильно будет.
Спасибо. Это все она демонстрируется уже?
Не, вам нужно нажать совместно с паузой. Включить микрофон.
Микрофон я вроде включил, да. Hello. So we are going to start. Now we have three members of this summer school. Okay, my name is Alexey Zhidyaev, and we are going to talk today about machining of materials. First of all, I'd like to say that if you have any questions about the subject, or questions, some maybe technical issues, or maybe questions about my pronunciation, you can ask your questions. So maybe I will correct or explain something if you need. Okay, this software is a little bit unusual for me. I'm using now different software for conference with students. That's why it's not easy to understand whether you are listening or not, or maybe there are some problems with sound. Okay, so machining of yes, hello. Machining of materials. And now, from the beginning, we are starting from the difficult, some complex picture and some complex explanation of material, but I will try to give some examples that will simplify this process for your better understanding. So machining or cutting, it's a group of processes and the workpiece is cut to form the final part by means of material removal processes. There are different types of processes to form some final shape of the part, and we are going to talk about cutting or material removing processes. So here you can see an example on the picture, of cutting process, and workpiece at the bottom is machined by cutting tool. You can see only the wedge, cutting wedge of the tool, which cuts some layer of the surface and forms the final surface of the workpiece. So some examples from real life, how to identify this process in real life. For example, you can imagine a process of slicing an orange using a simple kitchen knife, but it's also a cutting process, talking about different materials. But the better example would be an example of peeling an apple, when you peel or cut off the skin of apple. So our cutting processes are similar to this one. So we remove a layer of material from the workpiece. So we make, after cutting, we make our workpiece smaller, but we provide final shape and we provide final surface quality, better surface quality that we had before the machining process. So there are a lot of processes how to form the workpiece, but after forming the workpiece, we cannot usually achieve the final shape, and we cannot achieve the final surface quality on the workpiece. That's why we, let's say, add material on the final part, so our workpiece is thicker, wider, taller than the final part. That's why we need to remove some layers of material. Okay, also we can see that this is the picture that shows the movement of cutting tool. Tool moves to the left, or in some processes workpiece moves. In this case, if the tool is stable, workpiece moves to the right. And also we remove the layer of material, and after the removing, this layer of material is called chip. So it's usually some separate parts of the layer which are called chips. So you can see this chip here, this word here, and chip flow, the flow of cut surface layer. Okay, and this is an example of real machining. This machining process is called turning, and you can see here cutting tool, which is gold. It has golden color. Also, you can see the workpiece. This part of workpiece is the surface that was machined, and this part on the left, this part on the left is the surface to be machined. And after machining this surface, it will turn into chips. You can see chip here, one part of chip here. What are the processes? What are the main processes of machining? They are turning, drilling, milling, grinding, broaching, and some other processes, but main processes are listed here on this slide, and we are going to talk mainly about these processes. Of course, you can, after the presentation, you can search some videos on YouTube and see some videos about turning, milling processes, grinding processes. In this presentation, I will show only pictures, but if you're interested in this topic, you can watch some videos to to see some processes in action. Okay. The first example is a turning process, and here you can see a cutting tool you can see not only cutting part, and this cutting tool is black because it has different coating, different layer of coating on the tool itself relative to previous picture. That's why it's here it's black, so it's normal for cutting tool. And we have some tool holder for clamping and holding the cutting part of tool. And also we have some adapter to put this tool holder and tool into the machine, which provides the cutting process and the movements of cutting tool and the workpiece relative to each other. So this picture shows the workpiece, and workpiece rotates. So you can see here the rotation. I'm talking about the workpiece, we cannot see the rotation, but this fixture which clamps and holds the workpiece rotates. We can see it because the image is blurry. So workpiece rotates and cutting tool moves along the workpiece to form the rotational surface. So in turning processes, we provide achieve some rotational forms, which means they are cylinders, conical surfaces, toroid surfaces, spherical surfaces, and so on. Next process is drilling. And in drilling process, cutting tool rotates. And it moves along the axis of rotation to form the hole. So this is the cutting tool, which is called drill. The cutting tool is clamped in the tool holder. This is a thermo shrink tool holder. And the axis of rotation in this case is vertical. So cutting tool rotates and moves in vertical direction. So it forms the hole. You can see horizontal holes here, 6 horizontal holes. They were drilled in previous operations. And here we can see by means of these holes, we can see the process of the picture of the process of machining, drilling the hole. So this process provides us only holes after machining, holes of the diameter, which is equal to the diameter of the drill. So these 6 holes were drilled by bigger drill than the drill shown on the picture, shown in the picture. Okay, maybe you have some questions now. Maybe I should clarify something. Please, you are welcome to ask questions.
Oh, it's everything okay?
Okay. In this case, the next process is milling process. And milling processes are more complex comparing with drilling processes. So here you can see a mill or milling tool, and milling tool in the process rotates. This picture shows us shows the tool without rotation, so it's a picture when the process of machining was stopped. But we can see different inserts. So these inserts, 1, 2, 3, and I suppose 4 and 5 on the other side of end mill. These 5 surfaces, or these 5 inserts, are cutting inserts. So they cut the material, and they are also formed. They are also called teeth of cutting tool. So in the milling process, cutting tool rotates, and axis of rotation is also vertical, talking about this picture. And the cutting tool moves along the workpiece to make some flat or free shape surface. Flat surface, we can see flat surface here. This is the bottom of this part, and some free shape surface, some example of free shape surface is this inclined wall. This inclined wall of the part is an example of free shape surface. In this case, of course, you can say that the surface is not, let's say, good. It's not perfect. We can see something like leather here, or some rough surface. The bottom surface is also rather rough. Let's return to the previous picture. For example, this one, you can see a shiny surface, a very good surface after machining. So it's this surface can be used in some assembly of parts. So it's a good surface, let's say. Let's use this word. But this surface is poor or bad. Why? This is a rough process. So when we cut some materials, we usually divide the process of cutting on some steps. And the first step is a rough step, when we remove a thicker layer of material, but after the machining we have some rough surface. And after rough machining goes sometimes final step, or sometimes we can have medium machining and then final machining. But final machining process provides better surface quality. For example, we can see here we can see the process of final machining when we have the final shiny good surface. It doesn't mean that turning processes are for final machining and milling are for for rough machining. Every process, milling, turning, approximately every process can be divided onto rough machining and final machining. So this picture shows rough machining, and after this manufacturing step, there should be a final process of machining. The next process is, or next group of processes is a grinding group of processes. And here you can see cylindrical grinding process, which means that the workpiece rotates and also cutting tool rotates. And cutting tool also moves along the workpiece and forms some rotational surfaces, like in turning process. So we can form cylinders, conical surfaces, and some other surfaces of rotation. Grinding processes are usually final processes. So the surface after grinding is very good. The roughness of surface is very low, and this surface can be used for assembling different parts with each other by means of some ground surfaces after grinding. Another example of grinding is flat grinding. And in this case, grinding tool rotates. The axis is horizontal in this case. And also, grinding tool moves in horizontal direction to machine these flat surfaces of parts. You can see a lot of parts on the table here that are machined simultaneously. Okay, talking about previous pictures, here we can see chip flow, some separate chips that flows in machining process. In drilling process, we can see chip here. In milling, we can see only one chip, which was put only for making the picture, for making some good picture. In grinding processes, picture is chip is very small. I suppose you saw some grinding processes, some hand grinding processes with this process is usually called sanding. When we have a sanding paper and one side of paper is coated with particles, abrasive particles, they are similar to sand, which we can see on the beach. Moving this sand on the some surface, we can achieve some better finish, some shiny surface. And in this case, when we have a grinding tool, it also has particles, abrasive particles that are similar to sand, and they cut very small chips, but there are a lot of particles on the grinding wheel, and their size is starting from some microns and up to sometimes up to 1, 2, 3 millimeters. So it's a size of these abrasive particles that cut the material. So when we cut by particles with the size of some microns or tens of microns, we cannot see the chip because the chip is also too small. But when we don't use some cutting, cooling fluids, we can see these particles as sparks after machining. So this is a real process, and without using liquids, cooling liquids, we can see these sparks. So the temperature in grinding is very high. That's why chip, after removing from the surface, has a high temperature. That's why we can see the chip as a number of sparks. Okay. I'm started from the process, from the beginning. I tried to to explain the process, but I suppose it's a mistake. It was my mistake. This school is called Space and Technology. And of course, you think about some, let's say, rockets, some engine for rockets, some space vehicles, and so on. And in this case, I should maybe give you some information about using these technologies in rocket manufacturing processes. So every product and also a rocket and engine of rocket is a product, is an assembly, and this assembly is made of different units, and these units are made of separate parts, and every part should be made by some processes. And I suppose you some previous presentations were devoted to different processes of making parts, for example, welding, and also additive manufacturing processes, also some metal forming, bending processes, and so on. And material removal processes are also used for making some parts for rockets and engines of rockets. We usually divide this subject onto making a rocket itself and engines. So maybe we have different institutions in our university, and usually one of institutions is an institution that work with the vehicles, with the rocket, and another institution works with engines. So it means that we make a design, make some calculations of the processes, and also we make the technological processes. So it's a single chain of making the engine from design to manufacturing. And so does the faculty or institution of rocket engineering. So they have same steps in making the final rocket. So to make parts or to make the final product, we start from making different separate parts. And these processes, I'm talking about material removal processes, are used for making different parts. Of course, some other processes are also used in the manufacturing system. But a lot of parts are made using material removal processes. Then different parts are joined by sometimes mechanically using screws or bolts. Sometimes they are joined by welding or brazing techniques, and so on. So now I tried to give you a picture of place of these technologies in the rocket science. Okay, maybe now you have some questions. Okay. And now I'm going to talk about technological system, to explain what parts of the system are required to make some part for the engine or for the rocket. We need four main parts. They are machine tool, fixture or also clamping device, workpiece to make the final part, and also cutting tool for removing layers of material from the workpiece. So these are four parts of cutting system. Let's talk about these parts. Here you can see an example of machine tool. Machine tool, it's a kind of equipment that is used for machining. This picture shows an example of machine tool, but it's a complex one. It's a machine tool that can be used on big manufacturing plants where we can make some engines for example, for planes, for rockets, and so on. Of course, there are a lot of different machine tools. Small machine tools that can be mounted on the table for making some small parts, and some big machine tools for machining some unique parts, which would be bigger than this one shown in the picture. Okay, so, but also we can see all the system talking about this picture. Machine tool, in this case it is called Mazak, it's a Japan manufacturer. Here you can see a small fixture and clamping device. By means of this device, the workpiece is clamped. You can see the workpiece here. Of course, it's a static picture, so we cannot see rotation here. But this is a turning, it's mostly a turning machine tool, so workpiece rotates to form some rotational surfaces. Okay, this part is also a clamping device to hold our workpiece, our long workpiece from the right part. And here we can see the part of machine tool in which tool holder is mounted. Okay, tool holder is rather small here, but we can see this black tool holder, and it ends, tool assembly ends with cutting tool. I suppose it's a milling cutting tool here. So I told you that it's a turning machine, but we can see milling tool here. It's a complex machine that is called turn mill machine, which means that we can make, or we can realize, we can make a turning process on this machine, and also we can make milling process. That's why this machine is a very, very expensive machine. So usually machines used in manufacturing processes are a little bit simpler. So they are only turning or milling machines, or drilling or grinding. But this one shown here is a very complex machine, and we can make some different processes. Talking about this machine, this specific machine, you can ask why we use some different machines, turning then separate milling machines, drilling machines, and grinding. Why can't we use some complex machine like this? Because this machine provides turning and milling, and some kind of such equipment provides only also grinding processes. Of course, there are advantages when we make all the operations, when we make all the processes using one machine. But this machine is very expensive. That's why the some parts, when we need only turning machining for these parts, they will be too expensive if we make these parts using this type of machine. It would be cheaper to make a part with rotational surfaces using only turning machine, because simple turning machine itself will be cheaper. That's why machining using this machine also will be cheaper. That's why the number of these machines in manufacturing plants are usually not very high. So manufacturers also use separate turning, drilling, milling, and grinding, and other machines. Okay. Also, I should add, talking about this machine, that this is a multi-axis machine. And multi-axis machining, let's return to our previous processes. For example, this one. This process is a two-axis process, which means that cutting tool moves in two directions. It can move separately in these directions. The first one is horizontal and the second one is vertical, or in other words, axial direction, talking about the axis of part, and radial direction. These two directions are two independent movements of machine tool. And when we need to machine some cylinder, we use only axial movement of cutting tool and we form a cylinder. But when we are machining some complex surface, for example, this conical surface, we should use two movements, two movements at the same time. And these two movements form some, let's say, inclined movement, making conical surface. But talking about turning process, we need only two axes for making parts. This process is a process when we need only one axis, because we make hole only in vertical, moving in vertical direction. Milling processes usually require three axes. Talking about coordinate system, some coordinate system, the directions are X, Y, and Z, or two horizontal directions and one vertical direction. But this machine is multi-axis, which means that when we say multi-axis, we mean that there are 4 or 5 axes of movement. For example, here you can see that the cutting tool is in some inclined position because there is a rotation of horizontal rotation, and this cutting tool can rotate in clockwise and in counterclockwise direction. So I don't mean that the rotation of cutting tool which is required for cutting. I mean the position, initial position of cutting tool in machining process. So it's another axis. And also in milling process, the axis of rotation of the workpiece itself. It's a fifth axis. So these 5 axes are also very complex, and the control for moving all 5 axes the control is also complex. For example, if we are talking about this process, if we need to move in axial direction, if we need to move the cutting tool, we can make it by hand by some wheel, for example, if this machine has a wheel, or we can use some button. When we push the button, for example, for axial direction, cutting tool moves in axial direction. But when we need to move in 2 directions simultaneously to form, for example, a conical surface, we cannot push 2 buttons simultaneously, or if we push them, it means that the angle will be 45 degrees, but this angle is rather 30 degrees, looks like 30 degrees approximately. That's why to control this movement, we need special control for the machine. This control is called CNC, computer numeric control. And you can see here this computer numeric control. In simple words, I can say that this is a computer, but really it has, this computer has a link with equipment, electro equipment of machine tool. We see here a display, a screen, and we can see here some buttons for controlling, for programming machine, and so on. So mostly all machines are equipped with computer numeric control now, but there are also machines that are controlled by hand movement of operator, of worker. Of course, computer numeric control machines are more productive, and it is beneficial to use them in terms of productivity and in terms of quality of machining. But machines with hand control are also used in some processes. Okay, we are talking about technological system, and there are 4 parts of technological system. We've just discussed the machine tool, and now we are going to discuss fixture. Here you can see examples of different fixtures, of devices that are used for clamping the workpiece, for holding the workpiece. This is a 3-jaw chuck. Chucks. These chucks are used to clamp the workpiece, to hold it still. This is a fixture that is usually used for turning processes. This is an example of vise, milling vise. Also an example of fixture that can be used in milling, in flat grinding, in drilling, and some other processes. So we need these fixtures to clamp the workpiece. But also these fixtures are used to locate the workpiece in technological system, because when we have a setup machine and we make a machine on the first workpiece, after the machine and we remove the workpiece, and we take the second workpiece and we should put it at the same location. So the the designation of fixture is also to locate the new workpiece at the same position. And here you can see an example of an example of workpiece. On the left, you can see final part. This part is called blade. Usually separate blades are not used in rocket engine techniques. So blades are used in engines. Separate blades are usually used in aviation engines. In rockets, we have some different parts. They're usually called impellers with blades, and blades are, let's say, mounted rigidly on the part. And I suppose during some previous presentations, lecturers gave you examples of blisks, or they will give you some examples. So, but here we can see a separate blade. It's a final part. So it's a rather, it's not a blade for real engine. This part is called airfoil, and it is an airfoil from a real engine. And this part is root for mounting the blade in the engine. And this is not a real engine. It's not a real root, because it's this part was made for experiments. But later we will see some other pictures for this part. That's why I show you this part here. Okay, on the left, final part, and on the right we can see translucent workpiece. The top right picture shows the workpiece, and the top and the right bottom picture shows the part in the workpiece. So you can see where we have the material that should be removed to form the final part. Okay. So we discussed machine tool, fixture. You saw an example of workpiece, and now we are going to discuss some cutting tools. I can see that. I gave you about 15 minutes of lecture. Maybe now we should make a break. Do you need a break?
Maybe we
Yes.
could just continue.
No difference for me.
So if you don't need a break, usually lectures with some talking heads are they're tough, but if you are listening and you are full of attention, it's good. Okay, I will make a 1 minute break because I need to find a video file for showing you. So let's make a 1 minute break, okay?
Okay.
Так, что мы тут можем? Okay, everything is good. Are you ready? Let's proceed. So we are talking about part number 4 of technological system. And this part is cutting tool. This picture shows the example of turning cutting tool for turning processes. The insert is golden or yellow. By the way, which means that it can be changed because every cutting tool, for example, knife on the kitchen, after a number of cutting operations, every cutting tool will become dull, which means not sharp. Sometimes we can make a sharpened process for cutting tools, but for some cutting tools, resharpening cannot be applied. And this is the example, usually the example when we do not make some resharpening process. This insert is made of tool material. We will later discuss tool materials, but tool materials are very expensive. That's why we cannot make all the tool from tool material. We make only the insert, and basically the insert should be very small. On the other hand, to use less tool material. But on another hand, we should provide some strength, because if it will be too small, the strength will be too low and we cannot cut it by means of this insert. That's why there is a combination of strength and lower material usage. Okay, insert. Then tool holder, which is gray, tool holder to hold the insert. And this tool holder can be used in different turning machines. Tool holder is mounted in the tooling adapter. And tooling adapter is used or is chosen for a specified turning machine. So we cannot use, usually we cannot use this tooling adapter on some other machines or on every turning machine. But this tooling or this tool holder with the insert can be used on different turning machines. Okay, another example of cutting tools, and here we can see drilling cutting tools. This picture shows only cutting part of drill. Well, I suppose you saw drills. They are widely used at homes. I suppose you also have in your equipment some examples of tools. They used for drilling the concrete, for example, to put some picture on the wall, or to clamp some furniture and so on. And also they are used for drilling wood, but I'm talking now mostly about drills that are used at home. This picture shows drills that are used in metal cutting industry. You can see different cutting tools in different drills. And what is the difference? They are all for metal cutting operations. But this sharp, for example, this sharp drill on the right has a flute. This is the flute, helix flute of drill. This drill is used for soft materials when the drilling is and the chip is relatively bigger than for other processes. On the left, these two drills, the flute is smaller. The flute is smaller, and these drills are used for steels, for carbon steels, for for a lot of steels that are widely used in different products. Talking about these two drills, you can see that the flute is a little bit smaller, and also there are some additional geometry. These flutes are used for difficult to cut materials. what are they? For example, titanium alloys. For example, nickel-based alloys, and so on. No, I suppose we will discuss some design materials, some materials for products later. So you can see that, but you can see now that there are different geometries of cutting tools for different materials to cut. But all these drills have the same diameter. So after drilling, we will make one diameter, but drills should be used for different materials. Okay, next example shows different milling tools. For example, this one on the right is an example of cutting tool that we saw previously for milling process. This is the example of milling head with 5 teeth. 5 teeth here for cutting. We can also say, like in turning, 5 inserts. 5 inserts which are clamped by means of screws are used for machining, for cutting by this cutting tool. This picture shows only cutting tool. Of course, we will use milling adapter here to put this cutting tool into the machine, into the milling machine. On the left, we can see solid cutting tools. Solid cutting tools means that all cutting tool is made from tool material. So on the right, we can see an assembly with inserts, and only inserts are made of tool material. And the end mill is made of steel. And here, every mill is made of solid part, monolithic part of tool material. These tools also have some number of teeth. For example, this one has 4 teeth. This one has 6, and this one has only 1 tooth. Of course, there are a lot of different geometries of cutting tools in milling, and it's another topic, another subject, another lecture, or even some lectures to discuss different types of milling and also turning, drilling tools. I will show you only some basic examples. Okay, next example is an example of grinding tools. Let's go back to the grinding processes. Here we can see relatively small grinding tool. And here the diameter of cutting tool is bigger. So here I show only the examples of cutting tool and dimensions and also shapes of cutting tools differ. There are a lot of combinations of different cutting tool materials, cutting shapes, geometries, and so on. But also you can see here that this grinding wheel is made of some material similar to the sand. So you can see that it's not a solid part of some material. It's a abrasive cutting material which is, let's say, clamped by a special bond. Bond holds separate abrasive particles and forms the final shape of the grinding wheel. I suppose most of you also saw some examples of grinding wheels, because grinding wheels are usually used for some sharpening devices at home. Some simple sharpening devices which have only the rotation of cutting wheel, and the movement of workpiece is made by hands. For example, for sharpening some wood cutting tools or some other tools, sometimes knives for kitchen and so on. So such similar grinding wheels can be also used. But of course, these wheels are for serious metal cutting production. This part is devoted to part materials, or materials for our final parts, for our final assemblies, products, and so on. Simply, we can discuss next groups. Classification can be a little bit more complex, but for our purpose, we can use this classification. The classification is shown on two slides. So second slide, first slide. On the first slide, we can see carbon steels. Steel, it's a composure of iron and carbon. Carbon, the percentage of carbon is up to, let's say, up to 2%, and the rest is iron. In this composure, the rest is iron. Also, there are some alloy steels, and when we want to make some better materials, materials with, let's say, with better properties, we can add some additional elements in this steel. For example, nickel, chromium, titanium, aluminum, tungsten, and so on and so on, cobalt, vanadium, and so on. So all these materials, the percentage of these materials can be approximately up to 5% in all the composure. But they improve the properties of the steel. The next group is stainless steels, and this group, or steels of this group, have higher corrosion resistance, so they can be used in some aggressive liquids or in aggressive environment. The next group is aluminum alloys. Aluminum. It's a American version. In Europe, aluminum. It would be better to say aluminum alloys. So the alloys based on aluminum. Also magnesium alloys, and their main property is low weight, or parts made of these alloys have low weight. Okay, And this slide shows difficult to cut materials or difficult to machine materials. Now you can ask, if these materials are difficult to machine, why we use them? In terms of cutting, we should avoid using these materials. But in terms of final product, engine or rocket, we should use a lot of materials with improved properties, improved strength, improved weight to strength ratio, improved corrosion and other resistance, and so on. So we can mention here hardened steels. Hardened steels. Hardened steels are usually some carbon steels or alloy steels, but after special heat treatment. And this special heat treatment makes the steels hard to machine, difficult to machine. The next group is heat-resistant steels. They are based on iron, but they have a lot of special elements like nickel, chromium, cobalt, tungsten, and so on. So heat-resistant steels. The next group is heat-resistant alloys. These alloys can be based on nickel, or sometimes they can be based on cobalt, usually nickel-based materials are used. So what can we say about these two groups? When we can use these two groups of materials? They're usually used when we need to withstand, or the part should withstand high temperatures and also withstand corrosion of materials, of surface layer. So these materials can be used. For example, for next group, titanium alloys, they can withstand, some titanium alloys approximately can withstand temperatures up to 500 degrees Celsius and sometimes a little bit higher. These groups of materials, especially heat-resistant alloys, they can withstand temperatures of approximately of 1000 degrees Celsius and even higher sometimes. And of course, these temperatures can be achieved when some engine works. For example, in rocket engines and in aviation engines, sometimes temperatures up to approximately up to 2000 degrees Celsius can be achieved. So the temperatures are very high in engines, in some parts of engines. I can mention that special techniques of surface improvement are used to withstand high temperatures. So not only material itself withstands, but also some special treatment of surface of the part should be used. Okay, final group of alloys is a group of titanium alloys. This group, the main advantage of this group is a low ratio, low strength to weight ratio. which means that, for example, if we want to achieve the same strengths like for steels, the final weight of the part will be lower if we use titanium alloys. But titanium alloys are very expensive. That's why sometimes we cannot use titanium alloys. Also, they have boundary, talking about highest temperature they can withstand. So they have some restrictions, some boundaries in usage. Okay, it was a short excursus in part materials. Here we can see turning process of hardened steel. The part is made of hardened steel, and this shiny surface was machined, and this black surface is after heat treatment. So you can see that temperatures in machining are very high. That's why the chip has a high temperature, and it shines because it has high temperature. The temperature is close to melting point of this alloy. So that's why this is an example of difficult to cut material, because temperatures are very high. For example, if you are familiar with some wood cutting, I'm talking about wood cutting because wood cutting is a hobby for some of us, and we can sometimes make, for example, drill some holes in some wooden parts for our homes, for example, for some furniture and so on. And if you are familiar, you know that when you cut wood, temperatures are very high. That's why you should avoid excessive heating of the cutting tool. And if the heating will be excessive, cutting tool will become dull, not sharp. The same picture is with the machining materials for engines. If temperatures are very high, the wear of cutting tool will be excessive. So in this case, we will spend more money for making parts because tool wear will be very excessive. We would change cutting inserts, and that's why production will be more expensive. Okay, maybe you have some questions. То есть это не вопрос был, да? Okay, I thought it was a question, but I suppose it wasn't a question. Sorry for a second. А здесь есть чат какой-то?
Yes, you can add chat in the, yes, так точечку.
Ага.
Yes.
Ага. Спасибо. You can also use chat for writing questions. Спасибо. Okay, so we are going to talk about tool materials. What kind of materials are used for tools? First group is high-speed steels. And high-speed steels are relatively cheap. And talking about some tools for home usage, some drills or some usually drills are made from high-speed steels. So if you have some drills, they are made at home. If you have some drills, they are made from high-speed steels. High-speed steels were widely spread, let's say, in previous century, but now they're not widely spread, and the most spread group of materials is the next. It is the group of cemented carbides. Cemented carbides. Carbides are different carbides can be used, but tungsten carbide is a widely spread carbide. So it's these carbide particles are cemented by some bonding material. Cobalt is usually used as a bonding material in cemented carbides. For example, inserts for end mills, for turning processes that you saw on some previous pictures are made from cemented carbides. For example, all these end mills are made from cemented carbides. This insert is made of cemented carbides. Drills are usually made of cemented carbides, and so on. The next group is a group of ceramic materials. Ceramics are usually carbides, nitrides, and oxides, and borides. Ceramic materials are used for grinding techniques, for grinding cutting tools. So this grinding tool is made of abrasive particles, which are ceramic, and they are bonded by special bonding material. For example, resin bond, or some other types of bonds. Okay, these two materials are called super hard materials. They have the highest hardness known in the universe by man. They are diamond and cubic boron nitride. Diamond is a natural material, but in industry we usually use synthetic diamond. synthetic diamond. And cubic boron nitride is a synthetic material. So it was made in laboratory approximately 65 years ago. And the properties of cubic boron nitride are similar to the properties of diamond. But the difference is the next. Cubic boron nitride is used for and diamond is used for, no, let's say, approximately for other part materials. Aluminum alloys, also in wood industry and other types of materials. This example, previous example of turning hardened steel part shows the insert made of cubic boron nitride. Not all the insert is made of this material, but these two parts of the insert are made of cubic boron nitride. It's an expensive material, that's why also that's why it is used as a small part on the insert. So the part is made from steel, that's why we use cubic boron nitride here. Okay. And now I'm going to make I'm going to turn on the video, and this video file shows our manufacturing shop of our university, of our institution, and I will shortly talk and show some machine tools, some parts made on these machine tools, and some other topics. Okay, let me.
Я нижний должен еще раз составить. Слова снизу.
Ага.
Окошечко сведем. Просто сейчас выдаем презентацию.
Презентация? Okay, let's start. Sorry, we have some problems with the sound. Совместный доступ.
Сейчас прошу.
Can you hear the sound?
Он туда не идет.
I don't see
Галочка хорошо стоит, только не там, где нужно. Все, можем заново начать и показать. Так, только давайте сначала остановим, потом заново сделаем. YouTube. Да, совместный доступ звука, оптимизация для видеоклипов. Вот. И вы потом включите свой. И заново начнем, да?
Да, да.
Так.
Спасибо. Let's start from the beginning.
This is a turning machine, or it's also called a lathe. And this is a turning machine with milling function. So we can make a turning process for the workpiece with turning cutting tools. Or we can also set up a drilling or milling tool and make more complex part on one single machine. This is the setup on a milling machine, fixture on the table of milling machine, and workpiece, which will be the part after the machining process. And here we can see the real machining process. Milling machine cuts a part of a stamp, and of course we see cooling liquid here, and we don't see real cutting, but it's how the real process looks like. And here we can see the examples of real parts that were machined in our manufacturing center. These parts are for different devices, technical devices. For example, here we can see some parts for airplane, also micro engine, parts of micro engine, combustion chamber, shaft, some other parts. Also we can see here some tools. For example, this is an electrode machining a gear, so that's why it's made in the shape of gear. Also tools for forming some plastic parts. An example with also for production some gear, plastic gear. We can see real blades for aircraft engine that should be mounted into compressor of engine. Also we produce different cutting tools, tungsten carbide cutting tools by means of grinding technique. And also we can see some parts that were machined by students. In machine they made an impeller, a kind of impeller, and a blisk, and it was their project for their master's degree.
Okay, it was a short video about our manufacturing center in our university. Do you have any questions?
I have a question. So these process like the milling machine are used for mass production or just to create specific parts?
Thank you for your question. Yes, we can divide the production into, let's say, individual on one hand, and on another hand, mass production. Milling machines are used in different types of productions of production. But usually we are talking about universal and special machines. And for individual production, we try to use universal machine because in individual production, shape, dimensions of parts are usually differ in a wide range. And in mass production, shape and dimensions differ in low ranges. So I would better say that in mass production, parts machined on the that should be machined are very similar. Of course, I'm talking about one specific machine. So we machine on this part, for example, we machine on this machine, for example, something like, let's say we machine gears, some type of gears. And we have a lot of gears to machine. That's why this machine should be used for one type of gears or very similar gears. That's why this machine should not be universal, because the parts are approximately the same for machining. This machine should be special, and special machines are usually more automated. So the process on special machine is more productive. But this automation and productivity is achieved only because we machine one type of parts. We cannot achieve such type of automation and productivity when we machine individual parts. So milling machines are used for individual and for mass production, but they differ from each other in terms of, let's say, additional equipment of milling machine, additional systems of milling machine. Okay, thank you for your question. Do you have other questions?
Thank you so much.
Okay. And the next slide is devoted to precision. Every surface of the part has its precision. For example, you can take something like pen. Yes, we have a pen. Maybe it's not a best. Let's say we have a phone, and the phone has dimensions. For example, it has the width of the phone, and we have a drawing of the phone, and the drawing tells us that the width of the phone is, let's say, 7 millimeters. But we cannot make it 7 millimeters because our world is not ideal, which means we will make it, for example, 6 millimeters 0.99 or 7 millimeters 0.01. And this range between minimum and maximum is called tolerance. And every part, every surface of part has its tolerance. And some tolerances are tight. So, in other words, they are small. They can be starting from some micrometers and up to 10, 20 micrometers and so on. This is very tight tolerances. And some tolerances are not so tight. For example, they can be 100 microns and even millimeters. And for surfaces that are joined with each other, surfaces of two parts that should be joined in assembly, or for some working surfaces, for example, airfoil of the blade, which interacts with the gas while engine works. They should be precise. They are most precise, these examples are most precise surfaces on the parts. So we have a lot of, let's say, troubles achieving precision, achieving machining with tight tolerances. And I will show you an example. I will try to show you an example on the picture. The picture is a shaft machining. So we have a shaft. It's a simple shaft for presentation. So it's a cylinder surface that should be machined. So we have a workpiece with diameter, with some diameter, and after machining, the diameter will be smaller. These two gray parts are fixtures. We can see here a section in the part, and on the flangers of part we have two special holes for clamping. So these clamping devices, they are called centers, and next picture shows us a clamped workpiece. So the workpiece is clamped, and now tool goes to the diameter of cutting. The diameter of cutting and also the path of cutting tool is shown by this dashed line. So this is a trajectory of movement of cutting tool. This is the direction of movement. It is called feed direction. And also it's a turning process. That's why the workpiece rotates. RPM, rotations per minute. So which means that workpiece rotates around its axis. So our cutting tool starts the movement. And first of all, I'm showing you the ideal process. Cutting tool moves, and of course it cuts or it removes material, some layer of material from the workpiece. And here you can see chips flying off the cutting zone. So cutting tool moves. Okay, and finally we have the shape of our shaft. The trajectory of movement of cutting tool was a straight line, horizontal straight line. That's why we have a cylinder surface of the workpiece. It's an ideal process, but really, when the process of cutting starts, it means that we have a force acting on the workpiece, and from the physics, you know that the same force will act on the cutting tool. But the workpiece is not rigid, or rigidity of the workpiece is low. That's why by this acting force will bend, will deform the workpiece. And you can see here that the workpiece bends in a way like a smile. Yes. So the process proceeds, and we can see this bending this deformation, and the highest deformation will be at the center of the shaft. So here we have zero deformations, and deformation rises. Here we have maximum deformation, and here deformation falls. But what can we see? Due to deformation, the layer of material is thinner. The layer of material that is cut from the workpiece is thinner. So we remove less material. In other words, the higher the deformation, the lower will be the thickness of material which is removed. So here we remove with zero deformation maximum thickness, then the thickness of cut falls. Here we remove at the center minimum thickness, and here thickness rises, and here is also the maximum thickness, and as the same and as on the right part. Okay, so after all the machining process is done and there is no acting force, the shape will be like this. I call it, in Russian, we call it a barrel type error. So the real shape is not a cylinder, it's a barrel type shape, or shape with different diameters. Here we have one diameter, here we have maximum diameter, and so on. So this example, by means of this example, I try to make a to represent how actual workpieces and all the technological system behave during the machining. So of course we can see some shiny surfaces, we can see some let's say good parts after machining, but really there are a lot of errors after machining, and we cannot see these errors by means of our eyes. These errors are measured by means of special measuring devices. So of course here you can see that the shape is not a cylinder, but it's a picture, and it's a let's say magnified picture with magnified error. I especially made this picture with magnified error, with zoomed error. But really, after this type of machining, we will see a cylinder. But when we use a special measuring technique, we will see that diameters differ in different sections. So it's a, maybe it's a complex explanation, complex complex material for complex topic, but I want to say that there are a lot of errors during machining, and machining processes, like every other processes, are not very simple. Okay. So here you can see the difference between diameters in different sections. Minimum diameter and here maximum diameter. Okay, another topic in machining is micro machining. It's an interesting topic, and a lot of micro parts are made using this technique. Medical devices, some scientific equipment is made by these techniques. Here you can see a turning tool, and it's a turning tool with diameter, working diameter approximately 3 millimeters. But really micro machining starts from diameters on 0.1 millimeters. And here you can see a turning tool with a diameter of 0.2 millimeters. So we cannot even see the cutting edge, the part that cuts the material here. So it's a interesting and a very complex also technique of machining. But I would like to say these some words to you about micro machining. And this is a turning examples of micro machining tools. Also, we can encounter micro drills, micro mills for machining, for drilling and for milling. And some words about programming. What does it mean? Does it mean programming? As you remember, we use computer numeric control for machines. So the machine is controlled and all movements are made according to special program, which is called NC code, talking about machines. So first of all, we have a model of our final part. We make a model of cutting tool, and we, by means of special software, we make a trajectory of movement of cutting tool. These skylines are this helix skyline shows the trajectory of movement in machining this outer cylinder surface. After the trajectories are made, we usually make modeling of machining. So there is a workpiece in this software. This is the model of cutting tool. The yellow is a cutting part of cutting tool, and this is a holder of cutting tool. And you can see the machining according to the previous trajectory you saw. So this trajectory provides this machining. And this is another setup for the same part. You can also see cutting tool and some intermediate step of machining process. Rough machining, semi-finish machining, or medium process machining, final machining of the root. And after the machining process, modeling of machining process, we can see where we have some, let's say, problems or some uncut zones. For example, this is not the final step, but I show you here the example that we can see in orange parts that were machined and there are no additional thickness on the part, and blue lines or blue surfaces show that there are approximately 2.5 millimeters of thickness on these surfaces. So thank you for your attention, and I would like to ask you to answer your questions. Do you have any questions?
I have a question. Many of the topics you presented are also applied for conventional mechanical engineering or for just machining just pieces for the normal industries. And what is the greatest challenge in machining some elements, some pieces for aerospace industry, and what are the research in new technologies in this area?
Okay, thank you for your question. First of all, these techniques are widely used in different industries when we need to make some parts and then make some product from these parts. So, automotive industry, aviation, space industry, some tooling devices, even for phones, and so on and so on. So it's not some special set of techniques and processes. It's a widely spread processes. For example, I gave you some examples of metal parts, But also I should add that there are a lot of new materials, relatively new materials, like composite materials, carbon-based composite materials, with combinations with metals or with combinations with plastics. So there are a lot of new materials that can be machined using these techniques. So I can mention one challenge is machining new materials. And usually new materials, they have improved properties on the other hand, but on another hand, they are usually difficult to machine. That's why challenges are how to machine them, which cutting conditions should be used for machining, which cutting tool should we use, or even what geometry of cutting tool should be for machining these new materials. Another challenge is precision of machining. Why we make some new planes, some new rockets, cars, other devices. We don't make some new shapes, but we also improve these devices so they should go faster, higher, and so on. And for making faster cars, faster planes, rockets that fly higher, and so on, we usually should make new materials, and also we should increase the precision of machining. So it's another challenge, how to increase the precision of machining, how to make these parts with increased machining when the tolerances are very tight. So the tolerances are in range of some microns, micrometers, I mean, yes, micrometers. Another challenge that I can mention is is also with improvement of improvement of our products, final products. For example, we need to reduce weight of product, and in this case of reducing weights, parts become not so rigid, so that, in other words, they are flexible. And when they are flexible, no, not flexible is not a correct word. They are not flexible. They are not rigid, which means that if I take for example, my phone, it's rigid. I cannot bend it by hand. But let's imagine that there will be a machining process of milling of some part for the phone. It means that in milling, forces will be high and they will bend they will deform in machining this part. And on one hand, it's a lower precision, and on another hand, it's a question of vibrations. And vibrations are very problematic for machining process. So it's another challenge. Maybe I gave you not the overall list of challenges in machining processes, but there are a lot of research in cutting tools, in fixtures, even in machine tools, in cutting conditions, in special environments for cutting, for example, cooling liquids and so on. There are really a lot of research in metal cutting processes. Is it all, or I forgot to answer some part of your question?
No, that was all. Perfect. Thank you.
I can also add that there are you can see a lot of parts that were made without material removing techniques. For example, this is a bottle with water, and the bottle made of plastic was not made by material removing technique. It's another group of techniques for working with plastic parts. But for making this specified shape, special tooling should be used, and tooling is made from some metallic material, from steel. So to make this tooling, we should make material removing processes. Also, you can see mouse, laptop, some other devices. They are made from wood, plastic, or some other materials. But to form these parts, a lot of tooling is used, and tooling is made from steels, usually from steels or some other alloys. And all this tooling is made by means of material removing processes. So it's my addition to previous answer. Do you have other questions? You can see here my email. If you will have some other questions, you can write me. And if you don't have any questions now. So
I have one question.
Yes, you are welcome.
So how can we avoid the precision error such as the barrel error?
Oh, it's a good question. And there are a lot of techniques to avoid errors. One of the group of techniques is to find conditions of cutting, such conditions of cutting to reduce the acting force and to reduce the deformation. In this case, precision will be higher. But when we reduce cutting force, it means that we reduce the velocity of movement of our cutting tool. And in other words, it means that we lose productivity. But productivity usually should be high. Another group of techniques is choosing special cutting tools. And the third group is to apply special fixtures, or not special, but I would rather say additional fixtures. To make some additional fixture, for example, talking about shaft, approximately at the center of the shaft, we use additional fixture, which is called rest. Steady rest or living rest can be used to hold the shaft from the opposite side from the tool. So the tool was on the it was below. The workpiece, and the fixture, special fixture, should be under the workpiece. So there are special techniques to. There are some other special techniques, but the main techniques are as follows. I mentioned them. Okay. Do you have other questions?
Thank you.
Thank you for your attention. It was a pleasure for me to make a presentation today. And I suppose we end the presentation. Goodbye.
Thank you very much. Have a nice
Thank
day.
you.
Thank you. You too.
Bye. Thank you.
Bye.